Today we will discuss about a steady state analysis. In that we will discuss about some standard test signals and error constant and steady state errors. First we will discuss about what is introduction and related with material with that. Then we will discuss about the steady state error for a unity feedback system, steady state error constant and system types, is type number 0, 1 and 2, and then steady state error for the non-unity feedback system. First, we'll discuss about a steady state error. As its name implies, error means it is a difference between the input and the output for a prescribed test input as a time t approaches to infinity. Here it is. Here we are consider the step input signal and what kind of output we are getting for the input. Then whatever first we are getting the output 1, output 2 is getting the whatever the difference between that is nothing but a error. Next, same we have discussed for a ramp input also. A steady state error is designated by the ESS. Then we'll discuss about the test inputs. Test input is nothing but these are the different signals. By giving these inputs, we can find out the output. These signals are called as a standard test input signals. Actually, test inputs are used for the steady state error analysis purpose and the design purpose. Step input is nothing but it represents the constant position. It is useful in designing the ability of the control system to position itself with respect to a stationary target. Another input is that is a ramp input. It represents the constant velocity input to a position control system by their linearly increasing amplitude. And the third one is a parabolic input. It represents the constant acceleration input to position control system. It is used to represent the accelerating targets. These are the test inputs. First column shows the waveforms, that is a step input, ramp input and the parabolic input. Then the physical interpretation for that, a step is called as a constant position, then constant velocity and the constant acceleration. Time function for the step input, ramp input and parabolic is 1 t and 1 upon 2 t square. And then the Laplace transform for that one is 1 upon s, 1 upon s square and 1 upon s cube. One by one we will discuss. First one is a step signal. Here it is a r of t is equal to a into u of t. If a is it is a if t is greater than equal to 0 and it is a 0 if t is less than 0. The Laplace transform is a divided by s is there. And if for the step, if we'll consider the unit step, that will be 1 upon s as a is equal to 1. Same it is applicable for the ramp signal. For the ramp signal, r of t is equal to a t into u of t. Here it is. Then the function is a t if t is greater than equal to 0, the 0 if t is less than 0. Then r of s Laplace is a of s square. Next, parabolic signal. Function is r of t is equal to, reference signal r of t is equal to a t square into u of t. Then a t square u of a t square if t is greater than equal to 0, if t is less than 0. And Laplace transform for that one is a 2 divided by a divided by s cube. If we'll consider that here it is 2a divided by s cube is there. And if we'll consider the constant a is a 1, that is a 2 divided by s cube is there. Then the impulse signal is delta t, it's infinity for the t is equal to 0. And if t is not equal to 0, that is a 0. Laplace transform for the impulse is 1. And the sinusoidal is depending on the r of t, a or whatever the constant is there, a sin omega t. Laplace for that one is r of s is equal to a omega divided by square plus omega square. Next we'll discuss about unity feedback system. Here it is. To determine the steady state error, we'll apply the final value theorem. Final value theorem is f of infinity is equal to limit of s tends to 0 s into f of s. The following system has an open loop gain g of s and unity feedback since h of s is 1. Thus, to find e of s, this is the block diagram for that. Here unity feedback means feedback is not, only one is directly output is connected to the input. Therefore, E of s is equal to r of s minus c of s, and c of s is equal to r of s into g of s. And substituting the 2 into the 1, therefore E of s error is equal to is equal to r of s divided by 1 plus g of s is there. H of s is not there as we have considered the unity. Then next we'll apply the final value theorem. E of infinity is equal to limit s tends to 0 s into e of s. What equation we got for the e of s is r of s divided by 1 plus g of s. Then multiplied by s is there. Therefore limit s tends to 0 s into r of s divided by 1 plus g of s. This is the final value theorem for the unity feedback system. This allows the steady state error to be determined for the given test input r of s and the transfer function g of s of the system. Then we will apply that final value theorem for all the inputs: unit step input, then the parabolic input, then the third one is the ramp input. Then the first one is E error of infinity is equal to limit s tends to 0 s in is equal to step input 1 upon s is there, Laplace of that divided by 1 plus g of s. Means instead of r of s only we have put the value for the unit step, whatever the table we have prepared, in that Laplace of that unit step input is 1 upon s, that we have put here, and apply the limit. Therefore ss will get a cancel. 1 plus limit s tends to 0 g of s is there. The term limit s tends to 0 g of s, it's the DC gain of the forward transfer function as the frequency variable s approaches to 0. To have the 0 steady state error, limit s tends to 0 g of s should be is equal to the infinity. The next one is the ramp input. Ramp, that is r of s is 1 upon s square. We have put that. Therefore 1 upon limit s tends to 0 s into g of s is there. This is the steady state error ESS for that ramp, is that is nothing but a limit s tends to 0 s into g of s is infinity. If there are the no integration in the forward path, limit s tends to 0 s of g of s is equal to 0. Then the steady state error will be the infinite. Next for the parabolic, s in bracket 1 upon s cube is there, divided by 1 plus g of s is there. S square s will get a cancel, 1 s will get a cancel, s cube is there, therefore 1 divided by s square plus limit s tends to 0 s square into g of s is there. Then limit s tends to 0 s square g of s, that is a steady state error for the parabolic, is equal to infinity. If there are the one or no integration in the forward part, it is equal to 0. Then this is the example for that. Here we'll apply the number of input, that is phi of t, phi t of t, and the phi t square e of t. This is the g of s is provided for us. Then formula we are having for the all three. ESS for the first one is a unit step, that is a 5 divided by 1 plus limit s tends to 0 g of s is there. G of s here it is a 5 divided by limit g of s. We have to put the limit for this one by putting the s tends to 0. Therefore here it is 120 divided by, then whatever the g of s you will get, that is 5 divided by 21 is there. By putting the values in the whatever the formula is provided for us, we'll get an answer for that. Then we'll discuss about a system type. System type is the value of n in the numerator or the number of pure integrations in the forward path. Here it is a formula for that: k into bracket s plus z1 in another bracket s plus z2 dash dash divided by s raised to n in bracket s plus p1 in another bracket s plus p2. Therefore, if n is equal to 0, this is a type 0 system. If n is equal to 1, this is a type 1 system. If n is equal to 2, this is a type 2 system. Here it is examples are there for the type 0. G of s is equal to k into bracket s plus 2 divided by s plus 1 into bracket s plus 3 is there. There is s term is not present, therefore the type 0 is there. Then the below second example, g of s is equal to k into bracket 0.5s plus 1 divided by s into bracket s plus 1 to s plus 1 in another bracket s square plus s plus 1, but s raised to there is a one term, therefore this is type 1. In the same way, third example is for type 3 system. Then here it is example is determine the type of the system. Then static error constant that limits the determine the steady state error, that is position constant. Then whatever the formula we have we got for by giving the inputs, that is a position constant, velocity constant, and that is called as error constant, that is denoted by kp, kv, and the Ka. Limit s tends to 0, g of s is there. Limit s tends to 0, s into g of s is there. And the limit s tends to 0, s square into g of s is there. Kp, Kv and the Ka. Then we'll find out that values for that for every input. Steady state error for the step input. Here it is R of s is equal to R upon s is there. Therefore ESS for step input is limit s tends to 0, g of s is there. Then here it is R divided by 1 plus limit s tends to 0, g of s is there. Then R of s is R upon s, ss will get a cancel. Here it is, therefore R is only remain. Here it is, we have put the value of R of s is equal to R divided by s, ss will get a cancel. Therefore position error constant is Kp is equal to limit s tends to 0, g of s is there. Therefore ESS is equal to R divided by 1 plus Kp. We have put here it is one form, that is a Kp for limit s tends to 0, g of s is there. Therefore position error constant ESS for the step input is R divided by 1 plus Kp is there. In the diagrammatically here it is also, it is shown input and the output and error is R divided by 1 plus Next we'll discuss about a velocity error constant Kv. Same we are going to apply, only instead of R of s is equal to R upon s, we are going to put R upon s square. Therefore s into instead of R of s, R upon s square is there. Then ESS is equal to limit s tends to 0, R divided by limit s tends to 0, s into g of s is there. One s will get a cancel, one is remain. Therefore ESS is equal to R divided by SS is equal to R divided by Kv is there. This is for a position error constant for the step function. Then the third one is acceleration. Steady state error for the step function input R of s. Here it is parabolic input is there, R upon s square is s cube is there. Then here it is 1s will get a cancel. Therefore R divided by limit s tends to 0, s square into g of s is there. Therefore ESS is equal to R divided by Ka. Ka is nothing but error constant for the position error constant, that is called as acceleration error constant. So this is the table, whatever the formula we have solved up, that we have listed all here. That is our type 0, type 1 and the type 2. We can find out easily for all the types. Then here it is analysis via static error constants. One example is provided. We can find out easily what are the answers for that. Phi of t is a step input, then the ramp input is there and the parabolic input is there. With the help of formula, the limit s tends to 0, that g of s, then s into g of s, s square into g of s. We can find out the answer for the Kp and the Kv, and then we can find out the error ESS for the step input, parabolic input and the step input with the help of these formulas. Then for the non-funny unity feedback also, we can calculate g of s and the h of s is given. Here it is for unity feedback, non-unity feedback. Here it is g of s into h of s. Then we have to consider, instead of only g of s, we have to consider the h of s also, and the same procedure we are going to apply for that also. This is for the ramp input, this is for the parabolic input. Then we can solve the problem with the help of that. Thank you.